NAD is required for mitochondrial energy production, and that's what we'll see here, starting off in the mitochondrial matrix, and more specifically in the TCA cycle. And what we can see is that NAD is required for flux or movement through the TCA cycle, as it's a required cofactor for conversion of isocitrate into alpha-ketoglutarate, AKG, and for conversion of AKG into succinyl-CoA. Now, as a byproduct of those two reactions, NAD is produced. 2 moles of NAD are produced. And that's important because NADH donates those protons to complex 1, which then pumps them out. And then NADH's electrons, its corresponding electrons, are passed through the electron transport chain, culminating in the production of ATP. Now, note that NAD declines during aging, and I should say might decline during aging because some studies show that decline and other studies don't. So it's not a ubiquitous finding across all published studies. But assuming that it does decline during aging, if NAD is low, less NADH will be produced. And that's important because if there's less NADH, we'll have less mitochondrial ATP production, at least through complex 1. So with that in mind, if we increase NAD, will mitochondrial function improve? Now, to test that, we can track NAD levels, and I've tested NAD levels now 26 times using Ginfinity's test. And if you want to do that yourself, there's a discount link in the video's description. But what about plasma biomarkers of mitochondrial function? So there are, and they are lysophosphatidylcholines, which have been associated with mitochondrial oxidative capacity or mitochondrial function. And these are lysophosphatidylcholines, which are in plasma, so plasma biomarkers of mitochondrial function. Now, lysophosphatidylcholines probably seem esoteric, and this is a new term, and this is the first time I've introduced them on the channel. So let's dive into what are lysophosphatidylcholines before showing the published data. So starting with phosphatidylcholine 18:0 and 20:4. So what does that even mean? So the chemical structure of this metabolite is shown here. It includes 2 fatty acids, fatty acid 18:0 or fatty acid 18:0, which is stearic acid, and fatty acid 20:4 or 24, which is also known as arachidonic acid. So the first number is how many carbons, the second number is how many double bonds. So in the case of 18:0, that's a saturated fatty acid, and 24, or arachidonic acid, that's a polyunsaturated fatty acid. So for this phosphatidylcholine, those 2 fatty acids are connected to a glycerol backbone, which is also connected to phosphorylcholine, or PC. You can see that phosphate group POOO-PO4 connected to choline to the right of that. Now, that doesn't answer our question, though. What are LPCs? Well, under pro-inflammatory conditions, proteins such as phospholipase A2 or PLA2 cleave off one of these fatty acids, thereby leading to, in this case, free levels of fatty acid 24 or arachidonic acid in blood, thereby leaving behind lysophosphatidylcholine 18:0 as shown here. And just to reiterate, this lysophosphatidylcholine then includes the glycerol backbone connected to stearic acid on one side, and on the other side, phosphorylcholine. So let's take a look now at that data where plasma levels of lysophosphatidylcholines were associated with mitochondrial function, which is what we'll see here. So on the left, we've got levels of LPCs, many different LPCs, starting from LPC 16:0, so this is the LPC that contains the fatty acid palmitate, all the way down to the LPC that contains the fatty acid that has 20 carbons and 3 double bonds. And then skeletal muscle mitochondrial function was quantified in vivo through the skin with phosphorus-labeled magnetic resonance spectroscopy. So essentially, they did MRI through the thigh to look at levels of phosphocreatine as they recovered after exhaustive exercise. And this is a well-established technique. I won't go into all the details in this video, but if there is a large enough demand to cover this on its own in a separate video, just leave a comment and we'll see how many people like it. If there's a great enough demand, I'll make that video. So starting with quartile 1, this was associated with worst mitochondrial function, and quartile 4 was associated with best mitochondrial function. And what we can see is that LPCs were lowest in quartile 1, associated with worst mitochondrial function, and they increased through quartile 4. And in terms of the significance, we can see that all of these LPC species, with the exception of 16:0 for now, were associated with an in vivo assessment of mitochondrial function. So from this, we can see that lysophosphatidycholine plasma levels are associated with in vivo and an in vivo assessment of mitochondrial function. Now, I can already hear somebody saying, why even look at plasma biomarkers of mitochondrial function? Just measure VO2 max, lysophosphatidycholine in association with VO2 max. So they did that. And VO2 max in quartile 1, the worst mitochondrial function, those people had a VO2 max of 19. And for people in quartile 4, they had a VO2 max of 26. And these differences were statistically significant as that p-value is less than 0.05. Now, I can also hear someone saying these are very low VO2 maxes. This is a sick population. But note that these data, this study, was in 73-year-olds. So let's take a look at the LPC 16-0 if this is indeed also a part of the LPCs being associated with mitochondrial function. And that's what we'll see here. So now what they did, the authors of the study did, and I'll leave the link to the study in the video's description for anyone who's interested, is they looked at the top quartile, quartile 4, and then grouped quartiles 1 through 3. And when they did that, we can see that now all of those 7 LPC species were significantly associated, including LPC 16-0, with mitochondrial function. So higher levels being associated with better mitochondrial function, as were all of the other LPCs on the list. And in terms of those positive correlations, in other words, higher levels of these LPCs being associated with better mitochondrial function, we can see the beta coefficient is positive. In other words, again, higher levels of these LPCs, that was significantly associated with higher or greater mitochondrial function. Now, the good news is that these LPCs can be tracked. And to do that, I've been using Iolo's at-home metabolomics kit. If you want to track levels of these and more than 600 other metabolites, discount link in the video's description. So now we can track NAD levels at least using Ginfinity's test, and we can track LPCs using Iolo's metabolomic kit. So now we can address that question of, is NAD associated with biomarkers mitochondrial function, which is what we'll see here. So this is what we're looking at. This plot is NAD plotted against the sum of those 7 lysophosfatidylcholines. And note that I grouped them all together as one because they're all positively correlated with mitochondrial function in the same direction. So with that in mind, for me, it makes sense to group them as one number rather than looking at them separately, where optimizing each of those 7 biomarkers may be harder to do than one singular number. So on the y-axis, we've got NAD levels, again, measured by Ginfinity, and on the x, we've got the sum of these mitochondrial function associated LPCs, again, tracked with Iolo's kit. In terms of the correlation, we can see that it's not significantly correlated. So NAD levels, blood intracellular in NAD levels, were not significantly correlated with the sum of these LPCs, as that p-value is greater than 0.05. So superficially, that would seem to be a null result. Is higher NAD correlated with biomarkers of mitochondrial function? It would seem not based on this data. But note that I've got one data point that may be driving this correlation. So is that an outlier? So mathematically, an outlier is defined as being 3 standard deviations from the mean, or average. So when taking that outlier out and taking the average plus or minus a standard deviation for the 12 remaining tests, we get an average of 121 plus or minus 17, which means that for an outlier to be considered an outlier, it would need to be greater than 172 micromolar, which would be 3 standard deviations from the mean. In this case, that singular point is at around 325 micromolar, which is higher than 172. So for sure, this is mathematically an outlier. But it may not be an outlier. So there's a lot more to this story, because having at least 3 times higher LPCs relative to the baseline is present in Alzheimer's patients, which is what we'll see here. So on the y-axis, we've got lysophosfatidylcholine levels as a percentage relative to baseline. So people had their LPCs measured at baseline and then 7.5 years later. In terms of which LPCs were measured, 4 of the 7 on the list are shown there on the x-axis. And then there were 2 groups. So we've got data for women and men in the 2 leftmost columns, and then women and men in the 2 rightmost columns for each of these LPCs that were diagnosed with Alzheimer's disease up to 7.5 years later. And what we can see is that for the women and men who were not diagnosed with Alzheimer's disease 7.5 up to 7.5 years later, we can see that their LPC levels stayed around their baseline, maybe even slightly increased, which suggests having good mitochondrial function, or even slightly improving it, may be a part of the story for resisting Alzheimer's disease, at least in this study. On the other hand, people who were diagnosed with Alzheimer's disease up to 7.5 years later had big increases for these LPCs, from 2 to 5-fold higher relative to their baseline. So going back to my data, maybe that's not an outlier. Maybe that's an early warning signal for some pathology that could happen. And I'm not sure if that's the answer. I'm not sure if this is test-to-test variability. Once every 13 tests, I'll get a sporadically very large result, or it's just an outlier, right? So I don't know which way the story goes for those three possibilities, but we'll see how this story plays out over time. For now, let's think that it's an outlier. So when removing that outlier, we can then address that question of, is higher NAD correlated with biomarkers of mitochondrial function, which is now what we'll see here, as this is NAD plotted against the sum of those LPCs over 12 tests without the outlier. Same setup, NAD on the y-axis against the sum of the mitochondrial function-associated LPCs on the x. And now actually we've got a significant inverse correlation, as that correlation coefficient is negative 0.59 and the p-value is less than 0.05 at 0.04. But these data are opposite of what you'd expect. The expectation is higher NAD, better mitochondrial function. These data suggest that lower NAD is associated with better markers of mitochondrial function, as higher LPCs would suggest better mitochondrial function. On the other hand, on days when I raised my NAD with NAD precursors, note that I can't get to more than about 30 micromolar without NAD precursors like nicotinic acid or NMN. So that's how I achieved those two data points there, with NAD levels around 50 and 60. Note that that's significantly, if you extrapolate downward, that's associated with, or would be associated with, worse biomarkers of mitochondrial function when considering that relatively lower LPCs are associated with worse mitochondrial function. So this too is the opposite of what one would expect. Higher NAD being, in this case, correlated with worse biomarkers of worse mitochondrial function, not better. So then it raises the interesting question, which goes back to, again, how much is optimal for NAD? Is it high with NAD precursors? Is it relatively lower? How can we assess the optimal NAD level? So I think using LPCs is one part of that story. So now also note that those two NAD tests, which I basically artificially increased with NAD precursors, I can't get them that high on their own without nicotinic acid or high dose NMN. What happens if I remove them? So now over 10 tests, we can see that basically there is no correlation for NAD with the sum of these LPCs over the NAD range from 19 to 32 micromolar. As you can see that the p-value is far greater than 0.05. So to address that question of, is higher NAD correlated with biomarkers of mitochondrial function, at least for me, through 13 tests, there are three possibilities. First, high NAD, in my case, seems to be correlated with lower levels of LPCs, which suggests worse mitochondrial function at my highest levels of NAD. On the other hand, intermediate levels of NAD and intermediate levels of LPCs, this might be the range for having good mitochondrial function. But even there, note that there seems to be an inverse U-shape where when my NAD levels were around 30 micromolar, that may be correlated with my best mitochondrial function, because as LPCs go higher, that's actually correlated with lower NAD. And I'm not sold yet on that story, but that's just what the data might suggest. And the third possibility is that outlier, where low NAD but very high LPCs may be associated with an increased Alzheimer's disease risk, at least based on that one published study. If you've ever wondered what's optimal for biomarkers, then I have a new Patreon tier dedicated just to that. It includes these 29 biomarkers, and this isn't the reference range. This is what may be optimal based on how each of these biomarkers changes during aging and their association with all-cause mortality risk, using 45 published references. There's now currently more than 2 hours of video content in this tier, and I plan on expanding it over time. So if you're interested in that, check it out. And if you're interested in more about my attempts to biohack aging, I post at least twice a day in two of these 5 Patreon tiers, sometimes 3 or 4 times per day. And before you go, we've got a whole bunch of discount and affiliate links that you can use to test yourself, which helps support the channel, including ultralabtest.com, which is where I get the majority of my non-metabolomic tests done, clearly filtered water filter, using that every day, at-home metabolomics, as we went over in the video, oral microbiome composition, still trying to fix the Serratia oral microbiome situation, and I'll have more on that at some point in a future video. NAD testing with Ginfinity, as mentioned in the video. Epigenetic testing with True Diagnostic. At-home blood testing with Cyfox Health, which includes GrimAge, which I'll cover in an upcoming video. Green tea, diet tracking with Cornometer, or if you'd like to support the channel, you can do that with the website, Buy Me a Coffee. We've also got merch, so if you're interested in wearing the ConquerAging or Diet Trying brand, as I've got on here, but note that this is not what you see in front of you. I opened up a new store with a couple new logos, but that store hasn't yet linked with YouTube. So if you're interested in getting one of these and the other logo, or want to check out that new store, just leave a comment and I'd be happy to direct you to that site. Thanks for watching. I hope that you enjoyed the video. Have a great day.